Our next presenter is Dr. David Whaley. He's a research academic at UniSA. He is an electrical and electronic engineer who works as a teaching and research academic within the Barbara Hardy Institute and School of Engineering at UniSA. He is part of a small team that work in the Sustainable Energy Centre, who currently conducts research on low energy housing and technologies. He has authored or co-authored 9 journal papers and 27 conference papers in these areas over the past 8 years. David also currently teaches a course regarding renewable energy technologies, the current power systems and the integration of both. Finally, David is a member of the IEEE, Engineers Australia. What's the IEEE?
IEEE, it's the Institute of Electrical Electronic Engineers.
Thank you. Engineers Australia and the Alternative Technology Association. I know that one on stage, yeah. David will discuss a recently completed small-scale research project that investigates the cost and benefit of retrofitting and improving the energy efficiency, in layman's terms, of star rating of existing small, we didn't need to use layman terms in this room, my bad, single-storey houses in South Australia that were built before the introduction of minimum housing energy performance standards. 6 houses were modelled in the Adelaide and Adelaide Hills climate zones, where 25 to 30 improvements were simulated for each house that significantly improved the base case star rating and improved the overall energy efficiency of the building envelope. Thank you, David.
So thank you for the introduction, Jess. Okay, so at the moment, we have a bit of a trend in this country. We're building more houses, we're building them larger. And at the moment, about 20% of our greenhouse gas emissions are attributable to heating and cooling, okay? So that represents, so of the 20%, 30 to 40% 20% of greenhouse gas emissions are from the residential sector, 30 to 40% come from heating and cooling. We've seen information from the Bureau of Statistics over the last few years that the number of houses with air conditioners installed is increasing, and we've also seen that there's a bit of a trend that we're getting hotter days as time progresses. We also know that air conditioners cause peak power demands in this state particularly. So what can we do? We're going to try and use star ratings, and that's what this project is about. So star ratings effectively allow 2 similar products to be compared, and we see these across appliances, both in energy and water. We're even seeing star ratings in food these days, okay? We do see them in houses as well. So the purpose of a star rating system is to allow you to compare 2 products and see which one's more energy efficient in the case of houses or electrical appliances. And I'll never understand how Nutrigrain gets 4 health stars, but anyway. Okay, so when we're talking about houses, we have the nationwide house energy rating scheme. New South Wales has its own scheme, the basics, which I'm not going to talk about. But the scheme, the NATER scheme, basically allows a thermal energy equivalent to be provided based on one of the 69 climate zones across Australia. And we see some star bands represented here. So anyone who's ever built a house or done significant renovations recently will know that if they build a house, it must be built to the 6-star requirement. Okay? So what does 6 stars mean? Well, it depends on the climate zone you're in. You might have to squint or come closer for those at the back, but it technically means in Adelaide, 96 megajoules per metre squared of thermal energy to maintain thermal comfort throughout the year. And this is based on typical meteorological year data. And just to make it fair, like I said, there are 69 climate zones in Australia. The thermal energy required per star band does change for each of the climate zones to make it fair. So I'm going to talk about South Australian houses tonight. So of the 6 houses, one of them is in the Adelaide Hills in the Mount Lofty climate zone, and the other 5 are in the Adelaide Plains. So just to put it into perspective, 6-star equivalent for Adelaide is 96 megajoules per square metre, and that is area adjusted. I won't go into that unless anyone has specific questions later on, versus Mount Lofty, which is 230. And that's a reflection of the different climate zone. It's much cooler up in the Adelaide Hills. So we can see here in the chart at the bottom that these numbers are non-linear. So going from 6-star to 7-star does not represent half the energy usage or another amount. Okay, it's a non-linear scale. We can also see in the bottom there that when NATAS was introduced in 2004, we had a 4-star requirement. That moved to 6-star in 2006, 5-star in 2006, and we jumped to 6-star in about 2010, 2011. And unfortunately, it's not moved since then. So what does NATAS do? It allows someone with the skills to input everything about the building physics of a house into a computer model. And this includes things such as the construction materials, the orientation, the types of windows, insulation, window size, and ventilation. It does not include anything about the appliances, such as water heaters and general appliances. Basically, and the star band range runs from 0 to 10 stars, and 10 stars represents a house which essentially requires very little or a negligible amount of heating and cooling throughout the year. And you can see there on the right-hand side that we do have a star rating system with houses as well. And just to show you that it's non-linear, this 7.7 star house represents or is equivalent to 53 megajoules per metre squared. Compare that to the 96 for a 6-star house, so it's almost half of the thermal energy required for heating and cooling. There are 3 main tools that can be used to simulate a house. We have Accurate, Sustainability, we have BERS Pro, the Building Energy Rating Scheme Pro, and First Rate 5. And I've just shown you an example there on the left-hand side of a house in First Rate 5, and on the right-hand side is Accurate Sustainability. So they both use the GNET engine, which was developed by CSIRO a while ago. And the idea is that once all the parameters of the house are input, it creates a scratch file, takes the local weather data information, and simulates, again, the thermal energy required to maintain thermal comfort at under a number of assumptions. So the purpose of this study was to look back. You know, we've got these new building requirements for new houses, but we have a lot of older houses in this country. In fact, in 2001, the ABS reported there were 7 million individually occupied dwellings around the country. That's a lot of houses before the introduction of minimum requirements. Seen through the literature that typically these older houses achieve low star ratings. We're talking 1 to 2. And remembering that it's a non-linear scale, that's a lot more energy, thermal energy required to maintain comfort compared to a new house of 6 stars. So there was large potential to save energy and also greenhouse gas emissions associated with these heating and cooling devices, given that they represent the biggest user in houses at the moment. So I will say up front that there are, of course, limitations to this study. This was actually given to a master's by coursework student, and it actually started as a project just to keep him busy, okay? But the results are actually quite fascinating, to the point where we submitted the results to a journal and it's been published in a journal. Okay, so I'm going to say this straight out. There are a number of assumptions assumed by NATAS, right? And we're not going to open that can of worms tonight because a lot of people don't agree with a lot of those assumptions. The other big assumption here is that the retrofits I'm talking about are installed perfectly correctly, right? Now this is a big one because a lot of builders don't do the job properly. And I'll show you some horror story photos at the end of the presentation. And just to give you an idea, we've done some studies in the university which show that for bad insulation, an air gap of just 5% is enough to reduce the effectiveness in the R value by 50%, right? So if you're building a house or getting renovations and your builder leaves gaps around the place, pull them up on it. I've recently built a house and had to do this every single day. right? They just don't get that these things are actually fairly significant. Okay, so for this study, like I said, we picked 6 houses, and the aim was to pick a general house from the 50s, 60s, 70s, 80s and 90s. So we had 5 to begin with, and then my mate, who's my +1 tonight, Jared, stick your hand up, purchased this house, and lucky enough, he was able to allow us to use this house. This is a 1930s house up in Bridgewater. So this is our Adelaide Hills case study. And you can see the model with the first rate 5 model in the bottom left there. So the idea was to create a base case for each of the 6 properties based on the information we had from either the floor plans or from other programs such as Google Maps. It was a best guess at these houses. We have to start somewhere. We have to make a number of assumptions. And in fact, we did actually work with the Sustainability House for 2 of these houses just to make sure that the student was actually building these house files correctly. So thanks to the Sustainability House, there's a few of you in the room tonight. So there were a lot of assumptions that needed to be made. And because we only had information about insulation for the roof for 2 of the houses, we assumed that there was no insulation, roof insulation or ceiling insulation for the other houses. We assumed that the roofs all had an angle of 26 degrees with respect to the horizon. Brick walls were all cavity. Insulation was only added in terms of the modelling to external walls, not the internal walls. And there's another bunch of assumptions there about foil insulation. Again, the big one is that the roof space was accessible and ceilings as well as walls, such that the insulation could be installed correctly. We noticed that one house, the house from the mid-1990s, had weather stripping, the rest didn't, and single glazed aluminium framed windows were assumed throughout. And this is what we found. We found that the star ratings for these base cases were generally pretty low. As expected, we've seen it in literature. A few people have done this in the past. Interestingly enough, the houses with the ceiling insulation, or roof insulation, of value of R1, had significantly better star ratings than the other houses. What I find particularly interesting about this chart is the house from 1996 is one of the worst offenders, according to this. And you would have thought that since the 1930s, building practices would have been improved by then. Okay, so here is some more of the assumptions based on the cost. And all of the costs presented here tonight were obtained from the Rawlinson's Handbook, and they were provided in consultation with a quantity surveyor. So they're not just made up numbers, they're actually picked from somewhere and adjusted where required to reflect installation costs, various tradespeople, etc. We can see from this chart here that there are a number of double glazed windows which offer similar performance, but there is a cost difference in some of them of 2 to 1. For example, the fiberglass windows, nearly $1,200 per square metre versus the timber one at the bottom for $620. We have the U value and the solar heat gain coefficients exactly the same. These windows will perform the same, but one is almost double the cost of the other. And this is important because I'll come back to that. When we talked about other costs, we assumed that ceiling fans were not also included in these houses. And the cost of ceiling fans is given there between $500 and $700, and also based on the size of the room that dictated the size of the fan. Like I said, weather stripping was only present in one house, and we assumed based on the size alone, so all of these 6 houses are 100 square metres or less, and therefore attract a small cost for weather stripping in the order of about $500. And there's just some more information there about the installed cost of insulation at different values. So this is where the fun begins, okay? I'm an engineer. I like producing complex graphs, but I'm going to go slowly, okay? I don't want to lose you guys yet. So on the bottom here, we have thermal energy, meters squared, megajoules per meter squared. And on the y-axis, we have the cost of retrofitting, okay? Let's just ignore that for the moment. And we can see a series of vertical stripes here, right, or vertical lines. These represent the actual energy per star band for the Adelaide climate zone. We can see where 1 star sits, 2 stars, all the way up to 8. Hopefully I haven't lost anyone yet, because it gets more complicated. Okay, so by the blue dashed lines, we now show the equivalent energy star rating bands for the Mount Lofty climate zone. And you can see they vary, obviously, because it's a different climate zone. There are different megajoules per metre squared. So for example, it looks like the Mount Lofty climate zone 6 sits somewhere in the order of the Adelaide number 3. Okay? But again, they do experience different climates, so they do have different values. Make it fair. Let's plot our base cases, right? So these are the cases based on our base models and our assumptions, and we can see roughly where they sit. They're all shown for a retrofit cost of $0 because we're assuming nothing has been changed to the house by this point. Okay? So the student who did this work, he was pretty tolerant, because not only did he go through 25 or 30 simulations per house, the very first time he did this, he went through about 150 per house, just to identify which things had the biggest impact on the house. And then he applied those to the other 25, 30 in the remaining houses. So once we start concentrating on these 25 to 30 situations, well, okay, let's take the simplest case first, just adding weather stripping and ceiling fans. We can say that we're spending about $3,000 to $4,000, but there's not much of an improvement in the star rating or energy. But once you start including other things, we tend to see some very interesting results. Okay, now this is fairly complicated to look at. What it shows you is that you can reduce the energy, thermal energy required significantly if you're willing to spend about $15,000. Let's turn that into equivalent star ratings. So we're now showing how much money is required to achieve a desired star rating. And you can see there by the dashed vertical line, this is our 6-star, this is the requirement at the moment. Now I'm particularly excited by this graph because it shows you if you have a target star rating in mind, you could use this trend line to confidently predict how much it's going to cost. Okay, I find that fascinating. Maybe others don't. If we turn that into, if we show the cost now as a function of the star rating, so this is the same as before, this is on the left, except we're just zooming in to a portion of it. We can also show that as a function of thermal energy saving on the right-hand side. So some people might be interested in how much energy they actually save, whereas others are just interested in cost. So I mentioned before that the cost of windows for similar performance or identical performance could be a significant factor. This is shown by the blue boxes there for a couple of the houses. We can see that you could achieve a certain star rating. Let's look at the orange house, which is the 96 house, in the low $20,000, or you could spend $36,000. And the only difference in these two is the type of windows that is selected, right? So you can overspend pretty easily. If you have a particular desire to have better looking windows than your neighbour, for example, it can cost you a lot of money, but for no improvement in performance, okay? And if we have a look at the dashed boxes in the red, that shows you the impact of increasing the insulation in the walls, ceiling, so going to the next level up. And that shows you that you can get a better star rating for a much smaller cost. Okay? So, I don't like using this phrase, but there's more than one way to skin a cat, okay? You can achieve different star ratings lots of different ways. But if you want to do it in a cost-effective manner, then you should think about where you're putting your money. There are lots of conclusions. I probably won't go through them all because you guys can all access this video later. But generally, what we saw is that older houses perform pretty poorly compared to new houses. We saw that in literature, we saw that with the base cases. We saw that there were trend lines. You know, you can predict how much money you can spend to achieve a certain star rating based on what you wish to achieve. You can significantly overspend, as I said, based on the types of windows. And there's more than one way to do it, okay? You could almost argue there's an optimized approach Okay. Oh, the most important thing is it's not just looking at double glazed windows or insulation. It's looking at them in a combined approach, right? We're talking about the fabric of the building. The whole envelope of the building is critical. Okay, like I said, I've got some horror stories to show you. So this is actually a colleague of mine who built a 6-star rated house. One night was changing the light bulb and thought, gee, it's actually pretty cold up here at the ceiling when the heat is on. What's going on? So this is about 3 years after he moved in. I don't know why it took so long. But anyway, head up into the roof space. You can see there is no insulation in many parts. In fact, when he questioned the builder, they said, oh yeah, we put the insulation up in the roof space. Well, technically they did. They just left it in the bags. Okay, so he's since called them back several years later and they have installed it properly. Whilst he was up there, he also noticed that his air conditioning ducting wasn't installed that well. Wow. So whilst he was heating his roof space pretty well, it was actually racking up the dollars. Okay, so this was, I said before that it comes back to the installation. I was talking mainly about insulation, but you know, there are other things which should be checked from time to time.
Insulation, the air conditioner would have been quite good going down.
Well, it was heating, so it was going straight up. That's all I have to say.